tangent of beta L over Z naught plus J ZL tangent of beta L. Now, you all realize that that is the formula that I gave you, I think it was 2 lectures ago, last lecture we talked about it, right? Right? And this is a standard, well, maybe it was 1 lecture. This is a standard input impedance. Here's the tricky thing that people mess up all the time. See this beta L here? You have to make sure you do that right. And I recommend you do this in radians, not degrees. You all hear me on this? So if we take a look at beta, now just listen to me. When we're looking at the term beta L, well, beta is 2 pi over the wavelength. Do you all hear me? So make sure that's like rings true. So it's 2 pi over the wavelength. Here the length was given in wavelengths, not in meters, right? It was 1/10 of wavelength away, wasn't it? So they want the impedance when you're 1/10 of the wavelength away. So that would be lambda over 10. Do you all follow me? Now one thing that's obvious, the wavelength cancels. That's the idea. Do you all follow? All right, so cancel that. And now I have 2 pi over 10 or pi over 5, and this is radians. And that's important, because that's what goes here. Y'all with me? Now, you have Z naught, right? You have ZL, right? You can play games here. If you want to, you can do tricks by dividing top and bottom by Z naught. And you can get a normalized ZL here and make that just coefficient 1. But you can just brute force and stick this equation into your calculators, making sure the tangent will be done in radians. You all hear me? Now, some people, and I'm not against this, but you really have to know what you're doing. Some people will take this and they'll convert it to degrees and leave their calculators in degrees. You can do that, but I would recommend you just stay in radians, because everything will work better, I think. So go ahead and do this, and just tell me what you get. I bet you there's going to be people that get different answers. I just bet you. If you haven't done this problem, you mark my words, this is where errors are made with your calculators left and right. And if you haven't done them, it's almost a certainty you will have problems. For the quiz today, I'm going to separate everybody by at least 1 empty seat between you and your neighbor, probably 2. And do make sure you think through the calculations and do them carefully. Because this is where people make mistakes. So anybody want to give that to me? It's not a quick calculation unless you've done this several times. And if you have, what you notice is probably you want to have a memory for just ZL and a memory for Z naught, so you can just recall those values, and a memory for the tangent of beta L. .06 did you say?
Yeah, 15.06.
Plus
12, or J, 12.32.
Ohms, 15.06 plus J, 12.32. Who said that? All right, anybody else? I'm expecting some different answers. I'm not saying that's right. I've done this too many times. What did you do? Did you do it?
I was having issues.
Issues.
Yeah.
You're honest. You're gonna have a lot of quote issues. But get them out now. I mean, find out what's wrong now with your calculator. And if you have problems with a specific calculator, somebody here might be able to help you. That's another reason I like doing this. Your calculator's your best friends and worst nightmare too, all at the same time. If you know how to use it, they're great. But if you don't, you're gonna say, I knew what I was doing. My calculator did it. When I teach 3810, it's for non-AEs. It's the, like, civils and all. Their calculators are the single biggest angst that they have when they have complex numbers. They go bananas sometimes in their calculations. There are no wrong answers, believe me. I mean, there are, but right now what we're trying to do is figure out the scope. Anybody else got something besides this? You're probably afraid to say it, but please say it if you got something. issues, that's a good one. Anybody?
I got 2.47 plus J 1.12.
2.47 plus J what?
1.12.
Okay, let's keep going.
I got 24.7 minus 24.4J.
24.7, go ahead.
Minus J 24.4.
All right. Now everybody can see that we're getting a whole bunch of different answers for what appears to be a trivial kind of thing, right? I'm going to warn you about this right now. There's very little forgiveness on quizzes or tests. If you have this formula and you give me the wrong answer because you don't know what you're doing to calculate, you have to be able to get accurate calculations done if you're an engineer. Physicists can go ahead and just talk about, you know, abstractions, but engineers are paid to get the right answer because bridges fall down if they don't. And so we want to make sure we don't lose any more Mars rovers or anything like that because of a problem with calculations. Trust me on this, it's important to be attentive to detail and not sloppy or casual. So try it again. And then we're going to work in about give you another minute or two. I want to see if anybody else got, if you could confirm or deny any of the answers above. What did you give us?
24.7.
All right, so we got 2 here. Anybody else? Yeah, what'd you get? All right, so now there's another star. I have a comment about this in a second. Anybody else? Anybody else?
Yeah, 25 minus 24.18.
Minus J 24?
Yeah, minus J.
It's about this one, so this one right here is coming in strong right now. How much you want to bet that's the right answer? You know why? Because everybody gets a little paranoid and they start doing the calculations several times and seeing what answers they get. And I just bet that's the right answer. Now, what is the right answer? The solutions are there. Who asked me about this? Didn't you? What is the right answer?
Zn equals 19.19
19.19.
plus J 3.195.
That's what I got.
Well, somebody should have. All right, say that again.
19.19 plus J 3.195.
All right. So that's the right answer, and you see we get a whole bunch of different answers. I'm going to make one statement, and please hear me. The mistake usually is in the tangent of beta L. I told you to put it in radians. Some of you probably didn't. Then the next mistake is this. These two have to be summed first and stored before you sum these two and then divide. I promise you, you'll get this divided by this, and then this divided by this, not divided by the sum. Y'all hear me on this? This is a sum. I mean, you've got to do that and divide it. You've got to do this top operation first, then this bottom operation, then the division. All right? Now, I'm not trying to belittle your abilities. I'm just warning you. You've taught it too many times, and you don't really use your calculators for these kind of calculations that often anymore. You used to. So please hear me, okay? I hope I answered your question on that one. Was there another part to that or not?
No, that was it. I appreciate it. There's the degrees to radians.
It'll drive you nuts. And I don't know, everybody here have something like, do you have TIs, all you guys? I have HPs. I mean, I have an old HP. And, see, on TI, I think the default is degrees, if I'm not mistaken. I'm not sure. The 89s, there's an Inspire or something like that. I don't know. Most of these calculators have a default setting for when you do tangent and stuff like this, and I think it's degrees, but I'm not sure anymore. And be careful with the other thing I'm going to warn you about. Log. LOG of X on MATLAB, for instance, is natural log. On your calculators, if you have an LN of X and then an LOG, then you're safe. That LN is natural log, LOG is based on it. But I'm warning you, some calculators may not have that. Does anybody here have an HP calculator? You do? Here?
Yes,
Oh,
sir.
which one is it?
It's the HP Prime.
Is it, does that have LOG on it or LN?
Yes,
And
sir,
LOG?
both.
It has them both? Okay.
Yes, sir.
All right. All right, well, I'm gonna move on. Now, any other questions about the homework, since we're on and we found one that'll drive you nuts? Did y'all got this now, class? Did you have a question? Yeah, no, no? All right, wanna make sure. All right, now, out of curiosity, we have this. Could we find, if I gave you an input voltage, y'all know how to find voltage at the load there? Remember the complete circuit we did? Y'all remember that? All right, that kind of stuff you gotta make sure you know, but remember, for that problem, this is the thing that gives you your input impedance that you do voltage division with, right? So if this isn't right, everything else is wrong. Did you have to do complex calculations with real and imaginary numbers in any other class besides circuits?
Power, power.
Yeah.
In
Linear.
power? Okay.
Linear algebra is right here.
All right. So now, we're gonna go back to the Smith charts. I gave you some things to look at with Smith charts, and I think I gave you 1 or 2 Smith chart problems, right? Basic problems, simple problems. We're gonna continue on, and I'm gonna show you the true strength of Smith charts. Please watch this and listen. Part 2. So, when we have a Smith chart, first let me draw the circuit we're talking about. We're gonna have some ZL. We're gonna have some Z0 right here. And I'm gonna do this. I'm gonna say if we come down a length L away from the load, and we wanted to know what Zn is right here, we're gonna calculate it, but we're gonna use just the Smith chart. And you're gonna see it kind of relieves some stress because of that other calculation that we just did. It won't be as accurate, but it's accurate enough for anything we care about. So I like drawing a Smith chart this way, and if you have Smith charts, and I hope you do, and I hope you have a compass and a straight edge, and get them out. There you go, one. Now we're going to take a look at how we get the input impedance. We mentioned how to get the standing wave ratio, VisWire. But this is going to be all done using normalization. So whenever you have a Smith chart, the very first thing you do, by the way, let me make a few comments about what I call the general properties of the Smith chart, or things that are on there you need to know. The first is this. At this point is the reference of 0. This is the mile marker 0. And it also has an impedance of 0 right there. That's an impedance. If you look at your Smith charts, can everybody locate that point? You all see how it's 0, right? Now, if you go in this direction, this is wavelengths towards generator, go around. When you go exactly a quarter wavelength, or here, you'll see this is at a mile, or it will be at 0.25 will be the length and wavelengths. Take a look at that wavelength towards generator arch there. Can you all locate that? Now look, that's 0. You keep going all the way to here, you see 0.25, right? They might not have a lambda next to it. That means you went a quarter wavelength around. And you'll see this point has a value of infinity on it. Just follow me on that? Now, this is the R = 1 circle. And you'll see concentric circles like this that keep on getting smaller and smaller in the radius. The R values keep on getting larger and larger here until finally R goes to infinity and you're at a singularity right there. You all see that, class? Now if you keep going around, and you go all the way around here, you go back to the point that you started from, and now you've gone a total distance of a half wavelength. Now here's something to note. Every time you start at any point here, and you go around an entire circle, or go around there, 2 pi radians, or one trip, you move a half wavelength, you're back to the same point. So what that means is this. If I get a normalized impedance here, and I move a half wavelength away, it's the same impedance as it was here, or it would be ZL. So if it's ZL right here, if I move a half wavelength, it's ZL here. Y'all follow me in that, class? And every half wavelength that it repeats itself. So this is going to be important. Now those are sort of the general things you keep in mind. The north pole is at J1, that's where intercept is. And the south pole is at minus J1. You can take a look at those and just confirm what I'm saying. All right. Now we do a problem. And we're going to do the same exact problem that we just worked in class that he asked me about, only with the Smith chart. Y'all remember? And you're going to see it's a whole lot easier to get the right answer. So we start, when we have a Smith chart, the first thing we have to do is get the normalized load impedance, and that's going to be ZL over Z0. Now, and did you have a question? Okay, in our case, ZL was 25, right? Minus J25, was it? All right, so ZL, I'll put it here. 25 minus J25, and here Z0 was 50 for our particular. So I come over here, and I have 25 minus J25 over 50, or I have 1/2 minus J1/2. You all see that? That's point 1 that you're going to go into the Smith chart at. Now get your Smith charts and just try to follow me. I'll give you a second. How many have a Smith charts available to you right here? Good. How many have a straight edge? How many have a compass? Excellent, excellent. You can borrow your friends if you need it, but keep an eye on this one. All right, so we entered, where is 1/2 minus J1/2? All right, there's the one circle. The 1/2 circle is going to be about there. I'm just trying to estimate it. Locate that first. Y'all see it? How many see it on this Smith chart? It's going to be the big one, bigger than the one circle. It'll have 1/2 as the indicator on the trajectory. You all see it? Down here, you see it? All right. Anybody not see it? Next, you find minus J1/2. Now listen to me on this one in case you don't know. All the J's have lines that come perpendicular. Like right there is minus J1. Minus J1/2 is somewhere out here. I'm not exactly sure where, but you can take a look. So that trajectory will look like this. You all see that? Take a good look. And if you don't understand or don't see it, raise your hand and let me have somebody come over and help you. I want to make sure you all see. Do you see it? Everybody down here, do you see it? Or not? Okay, if you got to make sure you do see it. Now, where these two things intersect, the 1/2, the minus J1/2, that's the point. That is point 1/2 minus J1/2. That's point 1. Y'all with me? Now, take your straight edge. If you watched her video, she does a great job of this. And go from the center, right here, and draw a line right through this point. Like such. Take it right out through the edge. Like such. Y'all with me? Now, you're gonna see something, it will be on the wavelength towards generator marking, something in wavelengths here. You're gonna see something, it'll have wavelengths towards generator, blank wavelength. I call that a mile marker, like a highway mile marker. What do you read for there? What point is that?
0.412.
All right, 0.412, that sounds about right, and I'll tell you why. 0.412 lambda. Go ahead and take a look. How many see that? Right, remember, it's wavelengths towards generators. So now, this is important. All right? We're here, and we're going to move away from the generator, right? I mean, away from the load to the generator, towards the generator. We're going to move a tenth of a wavelength. Are you with me? Because that's what the problem said before, right? So now we're going to move. Now listen. Oh, I didn't say this. Take your compass and put the pointy end right there, and point the sharp pencil tip right there, and make a circle of constant radius. So it'll be something like this. Just do that. Now, that circle that I just put here on purple, that's at a constant radius, it's at this radius, which is the magnitude of the reflection coefficient. Do you follow me on this, class? That is a trajectory you're going to move when you add or subtract wavelengths to this load. Now, let me just explain this. This is the point we came in at, right? This is the allowable path we move on. Y'all follow me on this, class? So here we have to be careful we do this right. So when I take a look at this, now I notice that we're at 0.412 lambda wavelengths towards generator. I believe that was the location. Now we're going to add 0.1 wavelengths to it. So that means I'm going to have 0.412 lambda plus 0.1 lambda. That's 0.512 lambda. You all follow me? With me? Now, here's the important part. You see how I'm greater than 0.5 lambda? Anywhere in this circle, from wavelengths towards generator, I can have a value range of 0 to 0.5. Do y'all follow me? That's good. Zero's right here. When I go all the way around, I'm back to 0.5 or 0. Do y'all follow me, class? This isn't in that range, is it? So anytime you have a value after you added any distance from the load that is greater than a half wavelength, you subtract off the number of half wavelengths required to get this between 0 and 0.5. So now I simply subtract off 0.5 wavelengths. That would be 1 half wavelength, right? And now I get the point 0.012 lambda. Can you all follow me on this? Really what I'm doing is kind of obvious. I'm here, I've got to move to a point 0.512 that doesn't exist. So what I do is subtract the half wavelength and I land, if you can estimate it, I'm looking for the point with wavelengths towards generator that is 0.012 lambda. You might have to interpolate. A lot of times you are between two values. I mean, the value you're looking for does not exist in a sense, it's not stated explicitly, but there might be 0.1 and 0.2, so you can kind of extrapolate to 0.12. Can y'all follow me on that? How many see this point? I want to make sure you do. And as far back do you see it? Okay? And over here? Now draw a straight line from the center here out to this point. Just do it, please. And, can you all follow me? You go from the center of the circle out to where it says 0.012 lambda. Is that about where it is, class? Roughly? Probably up higher. I don't know.
Slow.
Lower? All right, well, wherever it is. Anyway, sorry. Now, locate this point right here. Can y'all follow me? The point that intersects that purple circle or the radius. You with me? What is the value here? Now, you're gonna have to use your eyes and squint. The Smith charts I gave you are pretty big, but you know, if your eyes aren't as good as they once were, like mine, get a magnifying glass or glasses. What do you get for that value, guys? Anybody?
.4, but there's
Zero.
there's a J
0.4?
component.
Huh?
There's also a J
Yeah,
component
what is that J component? The way you get it, remember, there are gonna be streamlines that come out through here, go through that point, and then bust up here,
It's
right?
like J 0.04.
J 0.04.
Right.
Anybody else see that? There should be a real value that's positive, that's small. And there should be an imaginary value that's gonna be positive and small as well. Anybody else confirm or deny that? What did you get, anyone? Anybody else?
You have to take this value.
Yeah.
And this is real.
Yeah.
And then you can go like this one.
Yeah, that's all, yeah. Anyway,
0.06.
Did you find that right there? Where's that-
Zero
where that's
six,
at?
all right,
Yeah,
this is
so it's
where
like
your
1,
eyes
2,
and your
3,
pencil
4.
thickness comes in. 0.6?
Yeah, it just depends
All
on
right, something
which
like
eye
that. Now
is
listen
right
to me.
here. Gotcha.
If you want the actual input impedance, that is the normalized input impedance, all right? To get the actual input impedance at this point, because this is where we move a tenth of a wavelength. The Zn itself would be equal to the normalized Zn that we got from there times Z0. So, would you do me a favor? The normalized value that we used was 50 ohms, wasn't it, class?
Yes, sir.
Take 50 ohms and multiply it by 0.4, and then tell me what you get, and then take 50 ohms and multiply it by 0.06. And that will be Zn. Zn normalized times Z0, or times 50. Just tell me what you get. 20 plus J3. Anybody else? Stop. What did we get on the prior problem? Wasn't it 19 point something plus J what?
0.19 plus J 3.195.
J 3 point?
3.195.
All right, you see how 3.1, we're close. Do y'all follow me? The error has to do with the thickness of your pencils, the ability to center things, and frankly, your eyes. Y'all follow me? But that is close enough for just about anything that you're gonna have to engineer. Anything else would be done in a different way. Y'all with me, class? So that's how you find the input impedance using a Smith chart. What would the Viswar be using this? First, if you have just remember, we got Viswar, we got what, standing wave ratio, right? And I think we got reflection coefficient. Now, this length right here, that is the length of the reflection coefficient. If you take it and then measure it against the bottom rail, do you all see in the bottom horizontal, there's a thing that says SWR? You can take it and put it there, but also you're going to see an angular measurement down here. And remember, we did that with the analog, we did it with the calculator, right? So what do you get for the reflection coefficient here?
Negative 116, 17.
Well, I mean magnitude.
Oh.
You need to take that and measure it. You need to take your compass or your straight edge, measure that distance, then take it down to the bottom of the Smith chart, the very bottom. You all see how you can get SWR on the very bottom? It's a measurement. You're gonna see a couple of things. It'll say either VSWR or SWR. Y'all see it? What do you get for standing wave ratio first? Is it about 2.6? Anybody check? What did you get, miss? 2.5-ish. Did anybody get that about?
Yeah.
You know where I'm looking, right? Right at the very bottom. So that's no angle there. It's 2.5-ish, 2.5 something, which is correct. Now, for this, you go down, the magnitude you get at the bottom, right? But the angle you get there. And somebody said it was 119 degrees, minus 119?
17, 16.
Minus 117?
Yeah.
So it's at minus 117 degrees, and what was the magnitude? Now you gotta measure at the bottom. Class? You guys get anything over there? Like, do you have the ability to do this or measure? You know what I'm talking about at the bottom of the Smith chart? You can get the magnitude, right? You take the length of this from here to here, and you go at the bottom, and it'll have reflection coefficient. The longer this is, all right, the larger the reflection coefficient. It goes all the way to 1, right? When it's this big. But ours is going to be, I forgot exactly. If you take a look in there, it'll be somewhere around 0.5-ish. What did you get? 0.46. Anybody else?
I got about 0.26.
0.26.
Yeah, I got
I
right.
got, see for SWR.
No. And 2.6 is the SWR. I'm looking for the magnitude of reflection coefficient, gamma. It'll be gamma on the bottom.
I got 2.6 as well.
2 points for gamma or SWR?
I got 0.56.
SWR probably.
Yeah.
All right, that's right. But look at gamma. What'd you get for gamma?
0.46.
0.46. It sounds about right. And I think if you look back at the prior problem, that's what we got. Y'all remember that? How many remember about these values for the last problem, where we actually did the calculations? Now this is a whole lot faster. Trust me, a whole lot easier. It brings you into the ballpark, and I'll tell you, it's really is pretty close. Okay? Unfortunately, I don't have enough time to go through matching, so I'm gonna leave it there, and I promise you a quiz. So would you do me a favor, everybody? We'll pick this up, and I think you'll be able to handle some of the things later.